Washington this summer.
Sometime.
We're going to talk about the real-time producer-consumer paradigm towards verifiable real-time computations. Kevin was telling me last night that when people think of real-time systems, they seem to be thinking of high performance. That seems to be the basic first reaction from people. So before you take your horse ride in a blazingly fast speed, you want to learn how to stay put in a saddle, and that's what is predictability. And Kevin thinks that's the more important issue. So the horses until Kevin talks about it. Theory and practice of temporal verification, I guess, before
yes.
That,
Thank you. Thank you, Chris. Well, that's interesting. Staying on that saddle, yes. So we'll see how well we can do. So this is the title of my talk and the title of my dissertation. And the key problem that I've been working on through the course of this work is how do you assess the temporal correctness of a real-time system? How do you determine what it does in time? To start off, I'd like to have a brief discussion on what we think a real-time system is. I think everybody has their own notion of what one is. I'll tell you what mine is. I think it's instructive to sort of look at some of the unique characteristics that real-time systems have. From my perspective, one of the more interesting ones is the existence of what I call event-driven performance constraints. And this is an observation that what most real-time systems spend most of their time doing are responding to events. You can think of these as some notion of these are what are loosely called timing constraints, if you will. The idea is that some event happens, either the arrival of an external stimulus or maybe some data structure reaching a particular value, and the system is required to take some action in a timely manner. Now, often the reason you require that this action be performed in a timely manner is because there's a high cost of failure associated with not performing the action. And in some sense, this is most likely what makes a real-time system real-time. If you didn't have this very high cost of failure, you wouldn't have to respond as quickly as you're required to. And often they exhibit a number of other characteristics that make your ability to design and reason about these systems quite difficult. They exhibit continuous operation in the sense that it's often the case that there's no set termination point for these systems that's known ahead of time. They have a high degree of physical and logical concurrency. If nothing else, these are just large concurrent systems. And they have often stringent availability, reliability, and fault tolerance requirements. So my view of the world is actually as a spectrum of computing. And you can index on this spectrum by any measure of whatever these characteristics you're interested in. And the one I'm interested in is time, as embedded in this notion of event-driven performance constraints. So within this spectrum, I'd like to focus in on one extreme, what has sort of been known as hard real-time systems. And in hard real-time systems, it's the case that the principal correctness requirement is strict adherence to timing constraints. The claim is that the cost of failure is so high that you will require that every instance of every timing constraint must be adhered to. And given this requirement, when you're analyzing a system, the principal property you're interested in is some notion of feasibility, where feasibility is a statement that says, given some statement of constraints and some set of resources available to you, is it possible to utilize those resources to convince yourself that these constraints will be met? Now, one question that you may want to ask at this point, and it's certainly something that I had to spend a fair amount of time convincing myself of, is do this class of systems really exist? Are there systems out there where the cost of failure is so high that you require this very, very strict notion of correctness? Well, the answer is I don't know. But it's been my fundamental hypothesis throughout this work that all real-time systems have some either component or subsystem that can be viewed as a hard real-time system. So we are actually solving an important problem. For example, if we look at this sort of prototypical air traffic monitoring system that I've shown here, this is a computer system that's responsible for monitoring a particular three-dimensional airspace and tracking airplanes that are flying through this space. The system consists of a communication subsystem that will communicate track information to neighboring airspaces, either saying, hey, this airplane is leaving my airspace and entering yours, or telling me that an airplane is entering my particular airspace. There's a radar that tracks things once they're in the airspace, and the computer is responsible for predicting where it will see planes next and managing this display console here. So if I put this up here and give you this informal description, I hope you're saying, yeah, this is a real-time system. These are sorts of the kinds of systems I think about when I think of real-time. Well, even within this real-time system, there in fact exist some very, very hard real-time subsystems. If you look at the communication subsystem, for example, I'm told it's the case that the type of subsystems that the FAA has are these time multiplex channels. And it's the case that if a particular air traffic monitoring system does not utilize its allotted slot on the channel, neighboring airspaces will think they're no longer alive and will no longer talk to them. So there's a very, very hard constraint over utilizing your allocated slot on the channel. That's sort of a constraint that originates in a hardware device. There are also some constraints that originate with the use of data. The computer is responsible for, given where a track was seen last, predicting where it will next expect to see an airplane so that it can tell the radar to look in that particular direction. Well, these radars are often very slowly rotating devices, so it's quite critical that when it's getting ready to sweep a particular area that you're interested in, where you expect to see something, that the computer tells it to make sure to have the appropriate energy so that it will scan out to where the plane is expected to be seen. So for this real-time system, there are a number of hard real-time subsystems. And if you were analyzing this system, you would want to know will these subsystems be feasible? And you want to know that given some information about the hardware you have available to you in these subsystems and some notion of the algorithms that are used, will it be possible to convince yourself that you will be able to get all your messages out on the channel in the right spot, and you will be able to schedule the radar so that all the tracks that you want to predict, you will be able to predict. So this is the problem that I'm interested in. It's this idea of trying to determine the feasibility of a real-time system. And this has sort of been the goal of most of my research. And my approach to dealing with this problem is I've defined a very simple computational model of what I believe what I believe a real-time system is. And I'll describe the model to you today in terms of a notation that I have, very simple notation for specifying constraints. It's a graphical notation. A very simple semantics that says what things expressed in this notation mean. And then based on the latter two, I'll be deriving a decision procedure that will allow you to determine, given some set of resources, will these constraints that you're interested in, will they be satisfied? Okay. Now, anytime you make a model of the world and you try and answer very precise questions about it, like I'm trying to do, things get undecidable very quickly. So in addition to understanding feasibility, I'm interested in trying to determine what's the most expressive model that I can make for real-time systems and yet still allow me to decide these questions that I'm interested in. And hopefully in the course of doing this, this will give me some insight into what's hard about this process of determining feasibility, and maybe give me some insight into what are good ways to express timing constraints and things like this. Well, I'm not the first one to try and deal with this problem of feasibility in real-time systems. People who have worked in this area have typically taken one of three approaches that I've listed here. By far the most popular is the development of a programming language. The idea here is you take some high-level concurrent programming language and you either augment the semantics or you toss in some novel synchronization primitives that somehow embody the real-time properties you're interested in, and you build a compiler for it. There's sort of been higher level approaches, more what I call design methodologies, and these have primarily been aimed at addressing the scaling issues that you can't write a huge air traffic monitoring system simply in one programming language. So these are trying to give you a grasp on the size of these problems. And lastly, there have been sort of more pure analytical models of the world. These have been either models of scheduling or program logics or computational models. The primary deficiency of most of this work that I'll try and actually give you a more concrete feel for later on in the talk is that they fundamentally don't address this question of feasibility. And I'll try and say exactly why that is later on in the talk. I view my work as sort of spanning somewhere in these latter two areas, that I'm primarily interested in doing an analytical study, but I'm also interested in ensuring that whatever I do come up with is not terribly abstract, that it would be possible to actually realize a real system based on my models. So that sort of concludes some introductory remarks. What I'd like to do for the rest of the talk is focus in on this model of real-time computing, and based on the model, show you how you analyze the model to determine its feasibility. To describe the model, I'll do it in terms of describing the notation that's used to describe the real-time constraints and the semantics to say exactly what this means. And I'll do the latter first. The semantics are loosely based on this paradigm of process interaction that I call the real-time producer-consumer paradigm. To understand this paradigm of interaction, we have to understand what is exactly a timing constraint. Sort of the big missing link at this point is what exactly is real time, and how does time creep into a program? So let me try now and give you a little motivation for exactly what a timing constraint is. Nicolaus Wirth, about 10 years ago, had this really wonderful paper where he gave a very natural sort of evolution of timing constraints. And he used the following example. Look at a standard producer-consumer subsystem, exactly that you would see if you took a first graduate course in operating systems. This subsystem has two active entities, a producer and a consumer, and they're synchronized by some passive entity that sits in between them. In this case, it's a horse-style monitor. And the idea is that the producer will produce some data that ultimately we'd like the consumer to consume. And we might not want these to go in lockstep, so we allow them to process asynchronously, and we have this synchronization object in the middle. And the way it works is a producer is conceptually running in an infinite loop, producing data at whatever rate it wants to produce data. And when it produces data, it tries to get it to the consumer somehow, and it does this by way of this deposit routine in the monitor. The monitor is implementing a set of buffers, and the deposit routine simply tries to fill up one of these buffers. Now, it may be the case that all the buffers are full, in which case the producer will have to wait. When one of the buffers becomes empty, it will proceed, fill up the buffer, and then signal the consumer to say, hey, there's at least one buffer that's full, in the event the consumer was waiting. The consumer, on the other hand, asynchronously is running around in its merry little loop, trying to remove data items as fast as it possibly can, using this remove procedure to remove things so that it can later consume them. Now, it may be the case that all the buffers are empty, so in which case the consumer will wait, and when it actually gets one that's full, it'll try and take it, but before it leaves, it'll signal the producer saying, hey, there's at least one empty buffer for you. Now, with this scenario, it's very easy to convince yourself that everything that the producer produces will be consumed by the consumer, and this is a very nice property for the system to have. Now, what if we try and sort of extend this paradigm of interaction a little bit into the real world? And that is, what if this producer object, for example, was a process in the real world? It's not a piece of software. Well, one of the ramifications of that is that it may not be possible to implement the functionality of this wait statement in the deposit routine for the producer. Because this producer is now something in the external world, it may not be possible that we can make it wait for us in the event that all the buffers become full. So in that case, if we sort of remove the wait statement, we have what I call a real-time producer-consumer subsystem. It's exactly what we had before, and we're interested in the same sorts of properties. That is, we want to convince ourselves that everything that the producer produces will be consumed by the consumer, but now we have to do it with the absence of the wait statement. So in this case, time has exactly come into the program at this point. In order to convince ourselves that everything that the producer produces will be consumed, we now have to reason about time. We now have to convince ourselves somehow that the consumer will be fast enough, if you will, to consume everything that the producer produces without the wait statement. So abstracting out this behavior a little bit, we have what I call the real-time producer-consumer paradigm. And it goes along the following lines. We have two active entities, a producer and a consumer. And a producer is sending data objects to the consumer. Now, if I'm some external observer sitting here in between the two, I can maybe measure the rate at which I see data objects flowing between the two. And maybe I'll measure this rate in terms of a worst-case inter-arrival time of the inputs. Now we have the following observation. If this rate at which I see outputs traveling between the two is realizable over an arbitrary interval, then it's necessarily going to be the case that there's no amount of buffering that I can stick between the producer and the consumer that will allow me to convince myself that everything the producer produces will be consumed. So in some sense, this system has to work with zero buffers, or it's not going to work at all. And what that says by having to work with zero buffers is that we'll require that the ith output of the producer be processed by the consumer before the ith plus first output is emitted. And this is what I call the real-time producer-consumer paradigm. Okay. So using this very simple notion of a process interaction, I have the following modeling discipline, following message passing modeling discipline. We have we have active agents, which are processes, and we have passive agents, which are data repositories denoted by the double circle. And they're connected via one another by communications channels of two flavors. A single-headed arrow is an asynchronous channel, and a double-headed arrow is a synchronous channel. And I'll explain a little bit more about what exactly these are in just a minute. But the fundamental abstraction that I'm presenting here is that when you have two processes that communicate with one another, say A and B here, A knows and is guaranteed to have as its behavior that every message it sends to process B will be processed by B in real time. That is, every interconnected pair of processes obey the real-time producer-consumer paradigm. So before I tell you why this is a good way of thinking about systems, let me describe these entities a little more in a little more details to give you a feel for the types of things that you can express in the model. We have data repositories that are passive objects. Data repositories are meant to model shared state. They're some type of state information that will be shared between a set of processes. They're connected to processes via a synchronous channel, meaning that when someone sends a message to a data repository, they will wait for a reply. A schema for a data repository is shown here. They accept a message, they do some processing, and then they send back a reply. And for right now, to keep the model simple, we'll assume that these don't perform any output. That is, they don't send out any messages themselves. Processes, on the other hand, are asynchronous objects. When you send a message to a process, you immediately continue on with the processing. And a schema for a process is that they'll accept a message, they'll perform some amount of processing, and they'll send out some number of messages of either flavor, either synchronous, meaning they'll send a message to another data repository, or asynchronous, meaning they'll send a message to another process. To get some idea of the way I believe the real world works, I have a notion of an external process, which is conceptually a similar process, except it doesn't receive any input. External process is something that's sitting in an infinite loop, sending messages to some internal process. And I'll make an assumption that I'll assume that an external process goes to sleep for some amount of time between sending messages. And for now, I want you to think of this duration which it goes to sleep as sort of a lower bound. Okay. One of the fundamental things I was interested in studying in this work was what was the effect of mutual exclusion on your ability to reason about feasibility. So I had to have some notion of mutual exclusion in the model. Plus, I also believed that it was necessary if this model was ever to be really useful. I've identified two types of mutual exclusion that I think are useful to talk about. The first one is what I call explicit mutual exclusion. You take some set of processes or some set of data repositories and just throw a box around them. And it simply means that processing of messages at processes inside the box must go on in a mutually exclusive manner. So A and B cannot be processing messages simultaneously. There's also a notion of implicit mutual exclusion, and this case arises when you have a process that receives messages from multiple sources. What this is meant to model is a shared service. C represents a service that is shared between processes A and B. And for consistency reasons, we'll simply require that C not process messages from A and B simultaneously. And I'd just like to point out that this mutual exclusion relation is completely orthogonal to the basic real-time producer-consumer paradigm. As far as A is concerned, A knows nothing about B, and A is guaranteed that every message it sends to C will be processed in real time, and B knows that every message it sends to C will be processed at real time. So we're not affecting A and B here, we're just simply restricting the way at which C will process messages. Okay, let's look at a simple example. Well, after trying to cajole you into thinking about hard real-time systems where the cost of failure is so high, it turns out that when computer scientists think of real-time systems, we like stopwatches. It's as hard real-time as we get. And David Harrell, in a very nice paper, sort of legitimized this example, talking about some of the interesting synchronization and timing problems that you find in something as simple as a stopwatch, or as a digital wristwatch is what he actually used. This stopwatch has two basic modes of operation. It's akin to exactly what you would have on a stopwatch on your wristwatch. It certainly has a stopwatch where it shows an elapsed time since you push the start button. And it also has a split mode where it will freeze the display to a particular value of time, and meanwhile, underneath the watch is accumulating time. To model it, I have the following simple design. There's two sets of devices. There's a set of watch buttons to turn the watch on, turn the watch off, put it in split mode, take it out of split mode. And then there's a timer, which is actually our external time reference. The timer will send messages to a process that I've called a tick server, and the tick server is simply responsible for distributing notions of real time to whoever wants it in the system. And the two people who want it are the stopwatch process that actually maintains the current value of the time, and what I call the flash timer. The way this watch happens to work, when the display is in split mode, the display is flashing on and off, and this is timed with this timer. There's a button process that fields the presses of the button, and depending on which button was pressed, it'll put the watch in the appropriate state and tell the display what to do. So why is this a good way of thinking about a real-time system? Well, at the very low level, what you know is that every interconnected pair of processes is guaranteed to obey the real-time producer-consumer paradigm. What this means is that, for example, with the tick server is guaranteed to know that the stopwatch process will process every message that it sends it in real time. And based on this very low-level style of interaction, there are a fair number of interesting questions involving time that you can answer about this type of design. Essentially, you can determine bounds for the temporal behavior along any path through this graph. And the reason this may be useful is, for example, you certainly might be interested in knowing that every button press will be received, but you also might be interested in knowing, well, what's the difference in time between the time I press a button and I actually see something happen on the display. I can give you bounds on when you will see something actually happen with the display. You might also be interested in sort of temporal properties of data values. You might want to know, for example, what's the maximum difference between the time value that's displayed and the internal representation of time, or maybe some external real-time value. Those are the types of questions you can answer about a program using this discipline. So at this point, there's at least two large open questions. The first one revolves around a notion of completeness. That is, can every constraint that you could ever hope to think of, can it be expressed in this modeling discipline? The answer here is not likely to be true. I know of at least a few types of constraints that you would like to express that do not map very cleanly into this type of discipline. I have actually done more realistic examples than the stopwatch, one of which I'll be showing you later. So although I may not be able to do every constraint, I know that I can in some sense do a rich enough set so that I can actually talk about real systems. The second question is, well, maybe I can't do everything, but even for the simple model of computing, how hard is it to determine the feasibility of it? That is, how hard is it to determine if every interconnected pair of processes obeys the real-time producer-consumer paradigm? And this is the question that I'm fundamentally interested in. And it will actually turn out later that in the course of answering that question, this will actually give me some insight onto this notion of completeness. In particular, we'll find out that it's rather hard to answer the question just for this simple model. And I can show that some straightforward extensions to it that you would like to have in order to allow you to talk about a wider range of constraints will actually make the feasibility process significantly harder than it already is. So what I'd like to do next is now go into a discussion of this feasibility. This is, in some sense, some of the theory behind how you determine what a program actually does. Now, to talk about feasibility, it's necessarily the case that you need some idea of what an implementation might look like. You need some idea of what an abstract machine is. So the first portion of the feasibility analysis is feasibility relative to a particular model of an implementation. And for historical reasons, this has typically been called schedulability. And what I need to do in this analysis is show you what a machine might look like that you would execute one of these things on, show you how the timing constraints map onto this machine, and show you how you can convince yourself that you will in fact meet these constraints. The second portion of the analysis has to do with what I call optimality. And the idea here is that ultimately I'm interested in those properties of programs properties that a program should have over all machines. That is, this is relative feasibility relative to a particular machine, and I'd like to know what is feasibility in a more global context, feasibility over all machines. So let's first try and understand what's a good model of an abstract machine for a real-time system. In order to do this, let's try and look a little bit more in detail at exactly what a process is and what a process does in this model. Well, processes are very simple things. They're things that just receive messages, process messages, and output other messages. Well, what I'd like to do is for every process and for every output channel of a process, I'd like to define what I call a transmission rate function. This is some function that will just give me a mapping from the rate at which a process receives messages to the rate at which it will perform messages. And again, I want you to think of these, every time I use the word rates, I want you to think of these as being defined in terms of a worst case transmission frequency. Now, because this model is rather simple, it's a very simple theorem to show that these transmission rate functions themselves are very simple. They're nothing more than linear functions with these harmonic coefficients. And to determine these coefficients, the way this is done is you find some underworked graduate student, and you give him the code for a program, and you say, tell me what this does. The way that I've chosen to do it is by modeling processes as finite state machines that make state transitions on message arrivals. And to determine what the coefficient is, it's simply a process of counting the minimum number, determining for a finite state machine the minimum number of state transitions that you have before you will actually see an output.
Excuse me, what's the set?
I'm sorry? Positive integers. Sorry. Okay, so let me give you an example of these transmission rate functions. If we look at the stopwatch, the example I have, we have the following functions. There's no reason this should make any sense to you. This is just the way what it happens to be for a particular implementation of it. If we look at the button process, for example, button process will receive a message when a button is pressed, and it will receive a message when a button is released. So it will take two messages, a down and an up, before it will actually perform any action. So its transmission rate function is simply 1/2 R, where R is the rate at which it receives messages. A process like the tick server is driving the stopwatch at exactly the resolution at which it sees messages. So its transmission rate function is simply the identity function. And just the way this system happens to be built, the flash timer goes at a rate 5 times slower than the stopwatch, so its transmission rate function is 1/5 R. Now, an interesting question is, for a process such as the display driver, I can certainly define its output rate. In this case, it just happens to be the identity. Every message that it receives, it will send something to the output. But what is its input rate? In particular, what is its input rate given that it receives messages from 3 sources that are most likely 3 independent sources? Well, for processes like this that receive messages from multiple sources, I simply define their input rate as the sum of the rates from each one of their message senders. So it'll be the sum of the rate here, here, and here. Now this may trouble you somewhat, because I've been saying all along, think about rates in terms of worst case inter-arrival times, and there's no reason to believe that at this point right here, such an inter-arrival time, that there exists a worst case inter-arrival time. If these are independent streams, it's very likely that I'll have simultaneous arrivals. We'll just sweep this under the rug for now, and I'll show you why this is a good assumption, why I've chosen to model things this way. We'll get around that in a bit. The abstraction I'm trying to present here is for each process is one of uniform arrivals, because I'd like to be able to analyze a process independent of who it's connected to. So the analysis for a process should be the same if it receives messages from one source or it receives messages from multiple sources. So I'll come back to this point and tell you why this is okay to put in this summation here. So once I've defined the functions, what I can do is I can start from the inputs and work my way through and solve these functions. If you recall, part of the schemas for these things was that for external processes was that there was some parameter that told me the minimum time at which a process would go to sleep between sending messages. So on the sources here, these inputs, I actually have constants. So I'll work my way through the graph, starting at the inputs, and solve all of these functions, all of these transmission rate functions. And by doing this, what I now know is I now know, in the worst case, how often a process has to be activated in some model of an implementation. So this gives me the following model for an abstract machine. What I have in one of these real-time computers is a set of sporadic tasks, where a sporadic task is defined by this three-tuple SCP. S is the release time of the task. It's the time a task will make its first request for execution. C is the computational cost or service demand. That's the amount of time it would take to execute this task to completion on a dedicated processor. And for historical reasons, P is called the period. P is a lower bound on the intertask request time. That is, if a task makes a request at time t, it'll make its next request at some time greater than or equal to t plus p. And the principal correctness requirement for a machine such as this is that we require that every execution request of every task must be completed within p time units after the request was made. So for example, if we look at this task here, it'll make its first request at time s, its next request at some time, say s plus p, and it'll keep making requests at an interval of p time units, although it may go to sleep for some amount of time. Sorry, I forgot to explain. The downward pointing arrows are points at which a task makes a request, and upward pointing arrows are times at which a task must be completed. So the goal of the system would be to ensure that each task gets C time units somewhere in the interval between the time it was made and P time units thereafter. This first statement that says it will make requests at least P time units after the next request, this is our statement of the way we believe the real world works. That external processes, for example, do go to sleep for some amount of time between performing some input. And the second statement here, this is our embodiment of the semantics, the real-time producer-consumer paradigm. We're saying once a task request is made, it has to be finished within P time units. That is, must do things in real time. So based on this model of a machine consisting of sporadic tasks, in order to determine feasibility, there are a set of scheduling problems that I now must solve. The first one is what I call the single producer, single consumer problem. These arise from considering a set of tasks, a set of processes rather, that have received, each process receives messages from a single source. And what I'll do is I'll make a decomposition from this higher level program into the tasking model. And what I'll do is for each process, I'll simply create a task. I'll give each task some starting time s, that in this case will be a random variable because I don't know, just given this information, I don't know when these tasks will actually start. They'll have some cost associated with them. I'll assume there's some oracle that tells me how long it takes to execute one of these processes. And for its period, I'll simply use 1 over its rate, where its rate is that parameter that that came out of the rate analysis from a few slides earlier. Now, because these receive messages only from a single source, they're independent tasks. There's a rather well-known result for a slightly more refined model of the world, due to Liu and Leyland, that says tasks such as these will be feasible on a uniprocessor if and only if the following quantity holds. What this quantity says is you can think of the ratio for each task, the ratio of C over P, as that fraction of the processor that you must allocate to task I over some interval of time. The ratio of C over P is the utilization of each task. And we're simply saying here that the cumulative utilization of the system has to be less than 1 because we're on a uniprocessor. And the algorithm that's used to sequence these tasks is called the earliest deadline first algorithm. The earliest deadline first algorithm simply says at every point in time, make sure you're executing the task who has the nearest deadline to you. And this algorithm is a preemptive discipline, and it's also been shown to be an optimal discipline in the sense that if any algorithm can satisfy the constraints on these tasks, this one can. Okay. Now I mentioned this was for a slightly more refined model. This is for a model where tasks are purely periodic. That is, once a task makes a request for execution, it will make further future requests at deterministic points in time. There's a very straightforward extension of their proof to handle my slightly more general model where tasks are sporadic. The more interesting problem comes about in the context of trying to deal with mutual exclusion. And on a single processor, we've solved this by looking at a class of non-preemptive algorithms. And again, we had two forms of mutual exclusion. We have two, each motivates a separate style of scheduling problem. The first one is exactly what we had on the previous slide, a single producer, a single consumer, but now we have a mutual exclusion constraint. These are tasks that each one receives messages from a single source, but now there's a box around them indicating that we required mutual exclusion. For these, I'll have the exact same decomposition as before. I'll just schedule them non-preemptively to ensure mutual exclusion, non-preemptively relative to one another. The second one, slightly more interesting, is this multiple producer, single consumer. These are processes that receive messages from multiple sources. And what I will do for this case is I'll replicate this process and create a task actually for each input channel that this process has. So for each input channel, I'll create a task, give it some starting time, which again will be a random variable because I don't know when these things will start. Since they all are performing the same function, they'll have the same cost. And again, for the period, I'll use 1 over the rate where the rate was determined previously. So I think you can see that this sort of gets around the problem of the simultaneous arrivals at nodes of this point. In some sense, what I'm doing is I'm using tasks to do some small amount of, to do a single slot buffer. By creating a task for each channel, we were assuming that on each channel was well behaved, that there was this minimum separation time. So as far as each task is concerned, there are no simultaneous arrivals. So this abstraction of uniform arrivals, that is the rate at which this process here receives inputs as being the sum of the rates, is valid. Now with these two, I need to now determine how hard is it to schedule these things in a non-preemptive manner. I have a new result that shows that the non-preemptive version of the same algorithm, the earliest deadline first algorithm, will be feasible on a uniprocessor if these two conditions exist. Now this is slightly more complex than the previous slide and unfortunately slightly less intuitive. The first condition is exactly the one we had before, and this is essentially the statement that the utilization has to be less than 1. The idea here is that the processor can't be overloaded. The second condition, the best I can do for you is to have you think of, assume these tasks are sorted so that tasks with a higher index have a higher period. And again, a period is the maximum duration a task can wait before it must be scheduled. So the left-hand side of this says, this is how long I can wait. The right-hand side of this is a bound on the worst-case blockage that a task can experience due to the fact that we're scheduling things non-preemptively. So we're simply saying that the amount I can wait has to be greater than the amount of time I'll be blocked. That's roughly what it is. Now, this worst-case blockage comes about when you have, it's somewhat intuitive, when you have, you're a very small task, and just before you make your request for execution, epsilon time units before you make your request, some monstrous task makes a request for execution. And because maybe I didn't know you were coming just a short time down the road, I start executing this big task, and because of this, you miss your deadline. It turns out that this is an optimal discipline for scheduling, but it's optimal only with respect to the class of algorithms that do not use inserted idle time. One way possibly to do better than what I've done is to intentionally idle the processor. For example, if you see a very big task to execute and maybe you know that maybe a little task will be coming just a few time units down the road, maybe I won't do anything. Even though there's a task that has an outstanding request for execution, I'll idle the processor and execute so that I can guarantee that I'll execute the small task that might be coming. It might be possible to do better than what I've done if you use that. If you don't use inserted idle time, this is as good as you can ever hope to do. I am not a particular advocate of inserted idle time simply because once all the tasks are executing, it's necessarily going to be the case that you'll have to trade off utilization, i.e. you're going to have to idle the processor when there was work to be done to gain feasibility. And that's not a trade-off that I'm willing to make. As such, there's no inherent limit on the utilization that you can have with task sets like this, other than you can't overload the processor. I also believe that given the small amount of non-determinism that sporadic tasks give you, that is, they can choose to go to sleep for some amount of time, that it might not be possible to constructively have an algorithm with inserted idle time. One last thing that I'll mention about this algorithm is that it shows out an important difference between sporadic and periodic models of the world. Previous to this work, it was the local wisdom was that sporadic and periodic models were the same. And in fact, they are the same for preemptive disciplines. Again, periodic models are one where tasks make execution requests at rigid points in time. Analysis of this algorithm has shown two interesting things. First of all, that there is no optimal algorithm for scheduling periodic tasks non-preemptively. And second of all, any algorithm that you would have to schedule these things, it's an intractable process to decide feasibility. So what this says is that sporadic models are, if you want to do feasibility analysis, you have to go towards more of a sporadic model. So this is some validation for the particular characterization of the world that I've chosen. So there are certain tasks that may be scheduled preemptively, sort of the single producer, single consumer class, and there are certain tasks that need to be done non-preemptively. In order to do the full analysis, I have to have some way of integrating these two, determining which ones can be done preemptively, which ones can be done non-preemptively, and sort of taking the cross product of the analysis on the previous slide in this one. I've done that work. I have an algorithm. The analysis is unfortunately much worse than this, so I'll spare you the gore and just tell you the result. The result is that you can take an arbitrary graph representing a program. For example, to date, this is the most complex example I've looked at. This is a naval data flight data preprocessor, done at Lockheed. I can take a graph such as this. In principle, one could automatically analyze this graph, that is, determine what needs to be done preemptively, what needs to be done non-preemptively, do this derivation of transmission rate functions, and then run it through some decision procedure based on my results in scheduling and give you a Boolean output. Boolean output being yes or no. When it says yes, what this means is that I will guarantee you that every interconnected pair of processes obey the real-time producer-consumer paradigm. And based on this, any type of information that you'd be concerned about how data flows along any path through this graph, you can come up with bounds on its behavior. So the interesting question to look at now is, so yes is good. Yes is a hard guarantee of its behavior. The interesting question to look at now is, what does no mean? When I run this through my decision procedure and it says no, what exactly does that mean? Does that mean that this is not feasible? Well, at this point, it's not clear, because again, what I've been talking about is relative feasibility. It's feasibility relative to a particular abstract machine, a machine that consists of a set of sporadic tasks. And what I'm really interested in is, what is the feasibility of this program as a program over all notions of an abstract machine? And it's very important to get an answer to this question, because in the event, ultimately, I constructed this thing and I wanted it to be feasible. So if my current scheme says no, I need to get some idea of where to invest my energy to make this thing more feasible. Should I go back and look at new scheduling algorithms? Should I go back and alter the semantics of the program? Should I go back and alter the program? What's going to give me the most benefit in terms of making this thing feasible? So what I'd like to look at in this last section is determine, again, what I call optimality. It was how good was this model of an abstract machine that I have. First, I'd like to see what's the relationship between schedulability, feasibility relative to this particular machine, versus feasibility over all machines. So I'd like to see if they're the same, and in the event that they're not the same, I'd like to determine how hard would it be to do any better than what I've done today. So let's first briefly look at the relationship between schedulability and feasibility. If we look at this very simple example of a process that will accept a message, evaluate some Boolean condition, and based on the evaluation of this condition, it will either send a message to process A or process A prime. Now, if A and A prime have the same transmission rate functions, then I think you can see that A and A prime will never execute simultaneously. It'll either be A or it'll be A prime, but they'll never both execute at the same point in time. However, as far as the abstract machine was concerned, it knew nothing about the structure of one of these graphs. And in particular, it had no way of knowing that A and A prime could never execute simultaneously. So when it did the worst case analysis, it was taking into account scenarios that will never occur in practice. So what this says is that so far, schedulability, as I've defined it, is a sufficient condition for feasibility, but it's not necessary. It's not necessary because it's considering scenarios that do not occur. So maybe I haven't done so well. What I'd like to now find out is, are there cases where I have done better? And if I haven't, how hard is it to do any better than what I've done? Okay. Well, it does turn out that schedulability, that is optimal. That is, schedulability is precisely equal to feasibility over all machines for graphs where subtrees rooted at decision nodes are n-ary trees with identity transmission rate functions. What does all this mean? N-ary trees means you have no sharing. There are no shared servers in the graph. Each node beyond a decision node receives messages only from a single source. Identity transmission rate functions essentially means there's no parallelism. Certain sections of certain paths along sub-branches cannot be executing simultaneously. So maybe this was intuitive all along, but now I have it says that the reason why it's not optimal is because tasks will share things and because they can execute things simultaneously. This may have been obvious, but now I have a very concrete derivation of exactly why that is so. So maybe I'm not optimal for any other type of graph. Well, how hard would it be to do any better than I have? Maybe you had a different model of an abstract machine. I've stated the problem as following. The primary reason for not being optimal has to do with potentially non-deterministic branching. What if I told you exactly how each program was going to branch? I told you I'm going to take this path 3 times, this path 4 times, this one once, this one twice. I gave you an exact characterization of its higher level behavior. Well, there is another model of a machine that will handle this behavior very nicely. The problem is that in that case, deciding feasibility is NP hard. And it's been an open question for some time to determine if this NP hardness implies intractability for this particular problem. In particular, it's not known if a pseudo-polynomial time algorithm exists to decide feasibility for this particular problem. So what this says is that there are certain ones where I've done as good as possible. And I think I convinced you that in any case I've done pretty good. And to do much better than I've done, between you and a better solution stands an open problem that you'll have to solve. So to briefly summarize this work, primarily what I've done is I've defined semantics for real-time process interaction based on this natural evolution of timing constraints. I have a simple very simple message passing modeling discipline for describing the behavior of real-time systems. And I've looked at the problem of feasibility analysis based on an abstract machine consisting of sporadic tasking. Some of the immediate conclusions that I draw from this work are, first of all, that the discipline works. It works in the sense that there are real systems that you can model with this and can answer questions about. It works at various levels in that, in principle, it can be applied to very, very fine-grained styles of interaction. In the stopwatch, processes were on the order of complexity of a few assignment statements, and in the naval example, processes were sets of modules, and messages were operating system service calls. I also now know that it is possible in certain cases to do an optimal feasibility assessment, and in any case, I know sufficient conditions for doing feasibility. I also know that feasibility is sensitive to the particular modeling restrictions, in the sense that I know it makes it hard. It's issues of sharing and parallelism. And I also know that one of the things that I didn't get a chance to mention today was that you can show that an arbitrary program written in this discipline is guaranteed to be deadlock-free. If you wanted to go to a more expressive model, for example, maybe you wanted data repositories to perform output so that you could construct hierarchical data repositories and get closer to a model of abstract data types. In doing that, you will lose this property. It is now possible for programs to deadlock, waiting for messages. The implication of this is when doing the analysis at the lower level of the abstract machine, it's no longer possible if things can deadlock to determine what's their worst case performance. So what this says is that there are things that map in the model, and to almost any obvious extension that you would want to make to this discipline will ruin your ability in a very severe way to perform this feasibility analysis. Some of the contributions that I hope the work will make is that I'm particularly fond of this semantics of process interaction, simply because I think it's well motivated, and you can understand an entire model simply by understanding these input arrival rates. I have the modeling discipline, which allows you to talk about real-time systems with precedence. I didn't get much of a chance to go into that today, but essentially it's implicit in the topological ordering of the graph. Resource sharing, mutual exclusion, and multiple processors. The two primary contributions are dealing with tasks that share resources and have mutual exclusion constraints. Multiple processors is interesting because your ability to answer questions about what happens to messages as they flow through the graph is a function of the number of processors you have. Basically, you're computing intervals, and you're saying the processing of a message will be somewhere in this interval. The tightness of this interval, if you will, is a function of the number of processors, simply being the more processors you add, the level of parallelism in a program goes up, and it's harder to determine what things are actually doing. So adding multiple processors might make the analysis easier in the sense that you're adding more resources, but your ability to determine what it does degrades slightly. I've also have a contribution which says on a single processor you can decide feasibility efficiently for these special cases, and again, in any case, there are sufficient conditions for arbitrary programs. And work done at the lower level of the abstract machine has yielded results in deterministic scheduling theory. There's the straightforward result of the non-preemptive scheduling, and an application of that to show how you can schedule a slightly different model of tasks that have shared resources. In the future, I have a whole list of things I'd like to do. The first one is further validation of the model with real examples. To my way of thinking, this should be validation, but my advisor said, say further validation. It sounds sounds nicer. It's been validated for a watch, and this a robotics system, and this Navy system. It's not clear how representative these are of the whole field. I'm very much interested in trying to determine if this modeling discipline is allowed for real-time practitioners. Does it allow them to express the types of things they're interested in expressing? Assuming I have some success with this validation, I now like to look at alternate forms of process interaction. I've primarily been looking at this domain of hard real-time computing and trying to understand what's the best you could ever hope to do in that domain. Most of the interesting problems lie more towards the center of this, more in the area of softer real-time. One of the ways that I'd like to move more into that area is to look at alternate styles of interaction. Essentially, the real-time producer-consumer paradigm is based on determining what's the behavior of a program for any two pair of messages. Now that may, and this is again based on this idea that what if this rate is realizable over an arbitrary interval? Well, what if it's not realizable over an arbitrary interval? Certain things are bursty in nature in the sense that you may get a very high rate of inputs for a certain period, but then you know that it's going to die off afterwards. I might get 1 a second for 5 seconds, but then I might get some period at which I don't see that sustained rate. I'd like to look at trying to model those types of systems. I have a pile of ideas on this, the most coherent of which is based on something I call more of a buffered real-time producer-consumer paradigm. The idea is not to look at any two messages, but look at some aggregate behavior. Look at some group of 10 messages, 100 messages over a 10-second interval. The analysis should scale quite nicely. The main technical implication of this is in the modeling discipline, you're looking at transmission rate functions with non-harmonic coefficients. I mentioned that right now I go in by hand with a big eraser and a very sharp pencil and try and determine what these transmission rate functions are. I would dearly love to automate this process. And the idea here would be what sort of restrict the programming domain a little bit. What types of language constructs would be useful for doing this so that these rate functions could be determined automatically. When you have an arbitrary graph, you can just as you can determine that certain things will never execute simultaneously, you can determine that certain things may execute simultaneously but will not interfere with one another. An implication of this is what this means is that you can, in some cases, coalesce sets of tasks into a single task. This does not affect your ability to analyze or reason about the system, but it would certainly affect the efficiency with which you could implement it. And I'd be interested in examining these rules. And the idea here, in some sense, is to determine what's the minimal number of tasks it takes to implement one of these systems. Another interesting problem is timing tools. I said somebody tells me how long something takes to execute. Well, nobody knows how long something takes to execute. So it would be very nice to get a handle on this problem without claiming to solve the halting problem. Architectural support for real-time scheduling. Many of the real-time practitioners that I speak with are not keen on the class of algorithms that I'm using for doing scheduling. They're a dynamic priority class, very simple, but it simply says that each task may have different priority at different points in time. People out there in the real-time trenches of the world deem these to be inherently inefficient for real-time work. I'd like to turn the tables around a little bit and say, look, these algorithms are really what you want to be using. They're elegant, they have a lot of nice properties, and they really aid your ability to reason about the system. Why don't we look at what type of architectural support you might like to have to make these as efficient as what you do now? Lastly, there's two rather dry problems in scheduling. There's still the open problem of does inserted idle time buy you anything? I'm skeptical, but I think there's one special case of it that might. And to really clean up all the loose ends, that's something I should look at. Lastly, when you go to multiple processors, you sort of lose the ability to do the feasibility analysis in an efficient manner, simply because most multiprocessor scheduling problems are intractable. However, there's still a need to solve those problems, and I'd be interested in looking at some scheduling and processor assignment heuristics for that problem. That's all I have. Are there any questions?
How does your model relate to queuing networks? In some respects, it looks like a special case where queues can have at most one element, and the arrivals are guaranteed to be separated by a time constant.
Arrivals from independent sources are, but once you actually go into a graph and after you've had shared nodes that receive things from multiple sources, they actually can have simultaneous arrivals. The general answer to your question is it's not related to queuing networks, and this is probably a philosophical reason that you really are interested for real-time systems about deterministic properties and not stochastic properties. I don't mean to be facetious, but if you're flying in an airplane, you don't want to know that the landing gear goes down 75% or 99% of the time. You want to have some degree of confidence that it will go down every time. So ultimately, at some level, the analysis takes on a very deterministic flavor. I guess what I'm saying is that it is my perception and a perception of others in the field, I believe, that the queuing network models do not directly address the types of problems and the types of questions that people want to ask about these class of systems. But that's not to belittle that work at all. Yes?
You expressed a reluctance to insert idle time because of the inability to achieve maximum utilization when you do that. And in the context of the model, that makes a lot of sense. If you think of any real system where you're modeling, where there are, of course, some stochastic fluctuations, isn't it a little dangerous trying to get too close to maximum utilization?
Well, that's a very interesting question. I'll tell you this, that the people who contract these systems agree with you. When you actually deliver systems to the government, there's some requirement, some mill standard requirement, I forget, that basically says, you have to convince me that in the worst of all possible cases, you'll never be above 50% utilization. So I guess, so you're right. In practice, that might be the case. Another reason for not wanting to look at inserted idle time is that there is some small amount of non-deterministic behavior in these tasks. They may make a request at some point in time, but they may not. And to use inserted idle time, you would be having to guess what the behavior of a task is going to be at some point in the future. And because of this, I don't know how to constructively use this information. I know that this will always work.
Well, is specifying 50% utilization time just changing a parameter? And,
Yes.
and everything will carry over in a straightforward way?
Yeah, essentially. Although it is the case that the lower the utilization, the easier in the sense that if you have a class if you have a set of tasks with arbitrary parameters, and there's two sort of phases. One is sort of utilization, and the other is your ability to meet these preemption constraints, those ugly formulas that I showed. There is a correlation between ability to meet the preemption constraints and lower utilization. Well,
There are refreshments in the lobby. Let's thank
Okay.
our speakers.
Thank you very much.